Hello, I'm Lou Bloomfield and this is How Things Work. Today's topic, air conditioners. An air conditioner does a remarkable thing. It removes thermal energy from the air in your home so that that air becomes cooler. But what does the air conditioner do with the thermal energy that it removes from your home air? Therein lies the big question. It can't destroy that thermal energy because energy is a conserved quantity. And it can't let that thermal energy flow as heat naturally because thermal energy flows naturally from hotter objects to colder objects, not from colder objects to hotter objects. And the room air is becoming the coldest thing around. So how does the air conditioner do its job? To explain that, I need to introduce the laws of thermodynamics. There are 4 of them, and I'm going to introduce the first 3. I'll leave the 4th one for some other class. The first 3, I'll name them and then I'll explain them. The first one is the law of thermal equilibrium. The second one is the law of conservation of energy. And the third one is the law of entropy. And that last one's going to be the key one, the one that we really want to pay attention to. The other 2 are not such a big surprise. So the first one, the law of thermal equilibrium. It can be stated in a bunch of different ways. So I'm going to pick one that's fairly straightforward. And here it is. If I've got 3 objects, red, purple, and white, say, and the first 2, red and white, are in thermal equilibrium, meaning they don't exchange any heat when I touch them. And the second 2 are in thermal equilibrium, meaning they don't exchange any heat when I touch them. Then, if I take the 2 red and purple and touch them, no heat will be exchanged. If that law weren't true, we would have all kinds of paradoxes, like we could have red giving heat to white, white giving heat to purple, and purple giving heat to red. It would be a paradox and we would have no way of predicting the flows of heat in general. The law of thermal equilibrium allows for a concept of temperature. And the purpose of temperature, a purpose of temperature, is to predict which way heat will flow when you bring 2 objects together and allow them to exchange heat, which way it'll flow naturally. So the hotter an object is, by temperature, the bigger the temperature, the more it will tend to give heat to everything else that's at lower temperature. In fact, just in general, if an object has if the red object's temperature is higher than the white object's temperature, we can predict with absolute certainty that the red object will convey heat naturally to the white object. Heat goes naturally from hotter to colder. And so the law of thermal equilibrium forms the basis for the entire concept of a temperature. All right, next law, the law of conservation of energy. Well, that sounds like nothing new. We know energy is a conserved quantity after all. But what the law of conservation of energy brings in is the recognition that thermal energy is energy. And when thermal energy flows from one object to another as heat, that heat is carrying energy with it. And that energy that's going with it is not that different from work. It's different only in the categories, in effect. It's still energy. So, again, the law of conservation of energy can be stated in many ways. And an easiest one would be to say that the energy of the white container here can be increased by doing work on the white container or by conveying heat to the white container. The energy going into it is simply the sum of the work plus the heat. It's often, the law is often written out in a more complicated way as the work in minus the heat out. But whether you subtract the heat going out or you add the heat going in, it's just fun and games with algebra. The idea is still simple. You can increase the heat of the energy of an object by doing work on it or by giving heat to it. All right, that's the law of conservation of energy. The final one that I will cover is really the crucial one for this story, and it's the law of entropy. And to explain the law of entropy, I first have to explain the concept of entropy itself. Now, entropy is a physical quantity. It's a measurable, well-defined, measurable quantity that objects have, or systems of objects have. And it's named a little unfortunately in English at least, because energy and entropy sure sound similar and are easily confused. And they are not the same quantity at all. Energy is the capacity to do work, so it's the conserved quantity of doing things. Entropy is not a conserved quantity. It's not about doing things. It is the measure of an object or system's disorder, how complicated the arrangement is. And to give you an idea of what I mean by disorder and order and stuff, I've got a bunch of dice here, a whole bunch of them. I could keep going all day. I've got hundreds of dice, but I put out a bunch of them, and I've arranged them in a very orderly way. Hope you can see. They're all pointing, they're one face toward you. They've got, of course, like any die, it's got 6 faces. Well, like any normal die, if you're not playing Dungeons and Dragons and stuff, it's got 6 faces, and these are all facing their one face toward you. Does that happen by chance very often? Can I just take a bunch out of the box here and just slap them down and expect to see that 1, 1, 1, 1, 1, 1? No. This is very orderly. It's something that's statistically unlikely and required effort. In fact, it required me to do something to make that happen. If I take them and I shake them up, will I come back with 1, 1, 1, 1, 1, 1, 1? No. It's possible, but it's so statistically unlikely, it will not happen. You want me to prove it? Okay, I will, of course. Okay, right. All right, line them all up, guys. And, oops, not 1, 1, 1, 1, 1. I could try again, it's never going to happen. What has happened now is the entropy of this collection of dice has increased. I started at a very low entropy arrangement. That is, the original arrangement of the dice, all ones, had very little disorder. As measured by entropy then, the entropy was low, small value. Once I scrambled them, the disorder increased. I now have a much more complicated to explain arrangement of the dice. The first arrangement, the low entropy arrangement, was one that I could explain with few words. I could say they were all ones. And now I have to tell you much more complicated. That the leftmost one is a 3, then a 4, then a 1, then another 1, then a 6, then a 6. And much more, the words, many more words, much more information I have to convey to you to tell you what this looks like. So high entropy, this is a high entropy, high disorder arrangement. High entropy arrangements are much more difficult to describe, to give all the information necessary to know how the thing is arranged. And what the law of entropy says is that the entropy of a thermally isolated system never decreases. Got a lot of words in there, but the basic idea is that entropy likes to increase. The statistics, it's actually driven by statistics, that things become more and more disorderly with time. The other words in the law are necessary, and here's the basic idea, is that if you have a confined system that is not allowed to export its disorder, that you build a wall around the system and make it thermally isolated. A thermally isolated system is one that cannot take the disorder that it has accumulated and send that disorder elsewhere, like taking out the garbage, okay? So as a system develops more and more disorder, if it's allowed to export its disorder, it can exchange the disorder with something else. For example, I could scramble all the dice, which is something that happens pretty naturally, and if I'm allowed to export and import order, which is to say I'm not in a thermally isolated system, I can cheat by taking a bunch of organized die. Here they are, getting there. A few more to go. And now, if the system is not thermally isolated, I can send out the junk and bring in the order. Waha! Look, I created a system that the disorder decreased. Wow! I have reduced the entropy of the system, but I broke the rule. It's not a thermally isolated system. I sent the disorder out and brought in order. Ha! I cheated. Okay, so the law of entropy says in a thermally isolated system, entropy never decreases. Well, why does it just say that entropy always increases? Well, because it is possible for the entropy to stay the same. Here it is. The entropy of this system is just staying the same. That's the best we can do, is not accumulate any more disorder. If I bring in anything that will allow the disorder to evolve, like my hands, entropy increased. And short of exporting it, I can't decrease it anymore. It's statistically unlikely. I cannot unroll the dice. So the law of entropy is observing that in these isolated systems, statistics drives the relentless increase in entropy. And the best you can ever hope for is not to have any change in entropy. You will not get it to decrease. The natural flow of heat from a hotter object to a colder object is driven by the law of entropy. Now, I've spent the past half an hour or maybe more trying to illustrate this using dice and stuff, and it's too hard. So I'm going to do it with words instead. So let me suppose that these two cans are a hot can in red, a cold can in purple, and let's watch the heat flow between these two. And before I do that even, let me remind you that the law of entropy says that the entropy of a thermally isolated system never decreases. Well, in this story, that thermally isolated system is going to be the pair of cans, not the individual cans. They are not going to be thermally isolated from one another. So the law of entropy does not apply to them individually, just to the team. All right? So my goal here is to explain the natural flow of heat from hotter to colder. So to do that, let me also tell you that thermal energy is itself disordering. So the more thermal energy that an object has, the more disorder and therefore the more entropy it has. So the hot can, the red can, has lots of entropy. The cold can, with little thermal energy, has very little entropy. So in addition to having different distributions of thermal energy, they have different amounts of entropy. All right, now I've touched them. And let's suppose thermal energy just randomly wanders from the red can to the purple can, from the hot can to the cold can. If that happens, the red can's entropy, well, first its thermal energy goes down a little bit, and its entropy goes down a very small amount. The thermal energy is already very disordering, and so losing a little bit of thermal energy, who cares? Who even notices? So the entropy of the red hot can goes down a little bit. The cold can, however, has very little thermal energy, and that thermal energy that left the red can for the purple can is very disordering for that purple can. A little bit of thermal energy added to a cold object increases its entropy a lot. So the hot can lost a little entropy, the cold can gained a lot of entropy. As a team, their total entropy went up. And the law of entropy is going, yay, this is what I want, this is what I expect. So when heat flows from the hot object to the cold object, the law of entropy is satisfied. The total entropy of the pair, and therefore the thermally isolated system, increases. What if entropy went the other way? From the cold can, not entropy, thermal energy, went from the cold can to the hot can. If that happened, so a little bit of thermal energy left when you touched them, left the cold can, went to the hot can. Well, that thermal energy leaving the cold can, which already has very little thermal energy, would order it a lot. Taking out a small amount of thermal energy from something that's already quite cold makes it significantly more orderly. It was orderly to start with, now it's really orderly. Okay? So the entropy of the cold can went down a lot. That thermal energy added to the hot can made it a little messier. It increased its entropy a little bit. It already had a lot of thermal energy. You add a tiny bit more. Who even notices? So the thermal energy, adding a little thermal energy to the hot can doesn't disorder it much more. Yeah, a little bit more, but tiny bit. So the consequence is, when thermal energy moves from the cold object to the hot object, the entropy of the cold object decreases a lot, and the entropy of the hot object increases a little bit. As a team, their entropy went down, decreased, and the law of entropy, absolutely not. This will not happen. It's statistically so unlikely it will not happen. And so we don't see that happen. If you take a cold can and a hot can, you touch them, it does not happen that the cold can gets colder and the hot can gets hotter. That violates the law of entropy, and it's statistically forbidden. So that means that we have a wood stove burning, cold room air, heat flows from the wood stove to the cold air. This is great. Law of entropy is happy as a clam. If you try to run this backwards, so got a wood stove, and in the summer you light the wood stove in the middle of the room, and you expect the air in the room to get colder have its heat flow into the wood stove. No, that doesn't happen. The law of entropy forbids it. So how do you make an air conditioner then? An air conditioner is doing the impossible job of trying to make the cold air colder than anything else around. And heat will not flow naturally into hotter stuff like the outdoor air on a sunny day, sunny, hot summer day. This is a problem. What do? Make a bigger thermally isolated system. Or at least be careful with the walls of the system. So if you put in another object, me for example, put me in the system, now I can start moving bits of thermal energy from one place to another with tweezers, at least in principle. And that, I can make the cold object colder and the hot object hotter, but I'm now part of the thermally isolated system. And the consequence of me suffering over trying to move thermal energy from one to the other is I start to accumulate more and more disorder. I'm using up order that I got from my breakfast cereal in doing the ordering process. And so as a team now, it's a team of 3. I'm part of it. And the team of 3 has its entropy increasing. But one of the parts has its entropy going down, the other part has its entropy going up, and mine going up. The overall entropy of the system is going up, even though we're making a colder object. So the system, these more complicated systems, you can actually still move heat. You can move heat from a colder object to a hotter object, but the overall entropy of the whole system has to go up. Well, for a realistic air conditioner, you don't get involved in it. What you do is you bring in order through wires as electricity. And the electricity arrives, it's electric energy that's coming in. And that electric energy is involved in moving the heat around. And what ends up, however, is the electric energy gets disordered in the process. And it increases the entropy of the overall thermally isolated system. So that although the room air gets colder, the outdoor air gets hotter, there is additional creation of disorder. And the additional creation of disorder is typically additional thermal energy added to the outdoor air. And that's really how an air conditioner does its job. It uses electric energy and the order that's present in electric energy to move heat from the cold air indoors to the hot air outdoors. And in the process, it turns the electric energy into thermal energy, which it also delivers to the hot air outdoors. So there is more heat delivered to the hot outdoor air than was removed from the cold indoor air. And overall, the entropy of the indoor air goes down, and the entropy of the outdoor air goes up, and it goes up enough because of the extra electric energy that's deposited and turned into thermal energy deposited outdoors. the entropy of the outdoor air goes up enough that the total entropy of the pair does not go down. In fact, it typically goes up. So more heat shows up in the outdoor side than was removed from the indoor side. Technically, how do they do this? An air conditioner typically absorbs heat indoors into a working fluid, and what a working fluid is a substance that we're not going to pin it down whether it's a gas or a liquid. It's a fluid, and the fluid goes to the indoor air where it soaks up heat. And then the fluid goes outdoors where it deposits the heat, it gives off the heat, and then it's recycled back and forth, back and forth. Now that by itself can't be enough, because that would violate the law of entropy. If the fluid were just going back and forth between those two all day and nothing else were involved, the entropy of the system would be going down as the cold air gets colder and the hot air gets hotter. So there's an additional process involved. The additional process in a real air conditioner, normal air conditioner, is a compressor that's electrically powered. And what is ultimately happening is the working fluid goes into near the indoor air as a liquid. So the working fluid, just to give you an example of a working fluid that could do this. Water could do this. It's not the typical working fluid that's used in air conditioners, but it could be water. If it were water that went in there, it would go in as liquid water, and it would in that location, it would evaporate to become gaseous water. It would then go outdoors as gaseous water, and it would condense to become liquid water and go back and forth. Liquid water to gas, gaseous water to liquid. As it goes from liquid to gas, it would absorb the latent heat of evaporation. As it went from gas to liquid, it would release the latent heat of evaporation. So it would soak up heat here, drop off heat here. Soak up heat here, drop off heat. Okay, but you need something in the middle to keep this to work and to not violate the law of entropy. And that something is a compressor again. And if we had water as our working fluid, and the real working fluids are now hydrofluorocarbons usually. They used to be freons, which were chlorofluorocarbons, but those were ozone depleting. And the hydrofluorocarbons are not ozone depleting, but they are greenhouse gases. So we basically want to keep them in the machines. Whatever these working fluids are, whether it's water again is a possibility that we don't normally use. You take the fluid as a liquid near the indoor air. You don't actually release it into the indoor air, you keep it inside a pipe. But you allow that liquid to evaporate inside its little environment. And you do that by exposing the liquid to low pressure, a low density gas above it. So now, if the liquid's present and there's almost no gas above it, the landing-leaving process favors leaving, and the liquid evaporates to become gas in this low-pressure environment. And in doing so, it soaks up its latent heat of evaporation from the indoor air and chills the indoor air. So now you have a gaseous working fluid. You're about to get outdoors, but before you do, you compress that gas. You squeeze it, pack the molecules tightly together, so the density of the gas dramatically increases. That packing process involves doing work on the gas. If you squeeze gas to high density, it involves pushing inward as it moves inward. That's work. So the result is the gas gets quite hot. It goes to high density and high temperature. So when it arrives outside, having gone through this compression process, it is very hot, high density gas. Heat flows out of it into the outdoor air because this compressed fluid is now the hottest thing around. So heat flows naturally out of it into the outdoor air through the walls of metal. You don't actually release the working fluid into the outdoor air, you release its heat into the outdoor air. So now, as the heat flows out of the gas into the outdoor air and the high density gas cools, it begins to condense. The density of the gas is so high, the landing-leaving process favors landing. And the gas lands on its own liquid, and the liquid grows at the expense of the gas. So now you have liquid working fluid again. And that liquid working fluid works its way, travels back indoors. It's at high pressure still as it's traveling back. And then it goes through a passage that drops the pressure. that releases the pressure and allows the liquid to be exposed not to high density gas as it was out here, but low density gas over here, and it evaporates again. So the liquid circulates back, the working fluid circulates back and forth with a compressor in between. Every time it arrives indoors, it arrives as a liquid at low pressure and evaporates. And every time it arrives outdoors, it arrives as a gas at high pressure and it condenses. And back and forth and back and forth. Well, the cold air indoors gets colder, the hot air outdoors gets hotter. That by itself would violate the law of entropy. So who's paying the piper here? The compressor. The compressor, because it does work on the gas in the act of compressing it, adds energy to the gas. So the gas is going from out of the evaporator indoors to the condenser outdoors. En route, it has energy added to it, and that energy originated at the electric company. And that energy ends up where? It ends up flowing out into the outdoor air as heat. So it's become thermal energy. So it started as electric energy, it ends up as thermal energy. And overall, there is more disorder sent outdoors than was removed from indoors. And the system as a group, as an entire system, a thermally isolated system, the entropy goes up, or at least doesn't go down. So the air conditioner can do this. The law of entropy says this is fine. You're following the rules. You're making more disorder than we started with. And the consequence is that the indoor air gets colder, the outdoor air gets hotter. And the outdoor air gets hotter by more than the indoor air gets colder. And it ultimately costs ordered energy coming in as electricity and ends up as that ordered energy ends up as thermal energy in the outdoor air. So that's an air conditioner operating. You can operate this same system in reverse during the winter. The outdoor air is cold, the indoor air is hot, and you want to make the indoor air hotter. So what you do is you run this as a heat pump. The air conditioner is technically a heat pump anyway, and if you run the system the other way so that it cools the outdoor air and heats the indoor air, it's still air. It's air conditioning the great outdoors at the expense of heating up your insides. What a sad thing during the winter when you want the insides hot. Obviously it's great, okay? And this costs electricity from the electric company in order not to decrease the entropy of the overall thermally isolated system. But this system now is more frequently referred to as a heat pump. It is actually heating the indoor air very effectively while using relatively little electricity. Why? Because if you use electricity to simply heat the indoor air by just turning the electric energy into thermal energy, easily done. Yes, it's 100% efficient. It's super, you get every bit of electric energy comes into the house, becomes thermal energy. But you can do better. And you do better operating this air conditioning unit in reverse, so-called heat pump, because if you buy say 1,000 units of electric energy, and you use that 1,000 units of electric energy to move heat from outdoors to indoors, you may actually be able to deposit 5,000 units of heat, have 5,000 units of heat flow into the indoor air. Where did that come from? 1,000 still came from the electric company, but 4,000 units of thermal energy were soaked up from the outdoors. So the air conditioner run backwards collects heat in its evaporator section. The working fluid evaporates outdoors where it needs its latent heat of vaporization. It soaks it up from the outdoor air, which is cold and becomes colder. And now the working fluid travels as a gas, is compressed by the compressor, and begins to condense indoors in the condenser, where it releases the latent heat of vaporization along with the extra thermal energy that came from the act of compressing the gas to high density. And so extra heat flows out inside. So you're leveraging the electric energy you purchased from the power company, from the electric company. You're leveraging it by using that electricity to move heat that already exists in the great outdoors, to move it indoors and release it indoors. All right, with that then, to summarize, to move heat from a cold object to a hot object, it will not happen naturally. So to cool the indoor air of your house, you can't just try to touch something else and have heat flow, because heat won't flow from cold to hot. Your indoor air won't get colder when it's touching hotter things. You can, however, move heat deliberately from the indoor air to the outdoor air or something else, but the consequence of doing that movement is you have to create enough disorder somewhere such that the disorder of any thermally isolated system never decreases. And the air conditioner does this by ultimately depositing more thermal energy in the outdoors than was removed from indoors. And the overall entropy then of the pair, which is not a thermally isolated system, the indoor air and the outdoor air are not thermally isolated, they're part of the same system. The overall consequences are the net entropy of the pair doesn't decrease. All right, and with that then, I will stop the story of air conditioners.